So we start off by defining just a normal curve. What does that mean? Um, if the random variable x is a normal random variable, i.e. bell-shaped curve, we denote it as x distributed. We just use n for normal. Some people write it out, doesn't really matter. And it has two parameters, mu and sigma. First, I just want to make sure you catch here, this is a little different than the binomial. The binomial, you had to identify if a scenario was binomial. That trips people up a lot, so make sure you feel good about that. We have to see a situation and ask ourselves those four questions. Does it meet those criteria in order for it to be classified as binomial? Obviously, if it's not discrete, then none of that matters. But if it's discrete, you might want to ask yourself those four questions. Say, is this binomial? For a normal random variable, how do we know it's normal? You got two options. Either A, it's going to tell you in the problem, or B, it's going to have a picture and it's going to be a bell-shaped curve. Or I guess kind of C, you could put those together. It could tell you in the problem it's a bell-shaped curve. There's no criteria to look through. There's no, does it meet this, does it meet that? It's just simply, it's got to tell you, or, normal or bell-shaped curve, or it's got to have a picture of a normal curve, which is a bell-shaped curve. Um, so no criteria to look at. We use the same notation we had before. That reads x distributed as normal. There's two parameters. Remember, the parameters for the binomial were n and p. Those were the two things that any time you said, this is binomial, you should always stop and say, well, what is n, what is p? And the same thing's going to apply here with a normal curve. Anytime you identify something as normal, again, picture, it's going to tell you, you need to identify, what's the mean, what's the standard deviation, right? That's what these two symbols represent. That hasn't changed. And so I just want to notate that here, where mu and sigma represent the mean and standard deviation of the distribution. This goes back to what we had talked about previously, which was we're going to oftentimes talk about the shape, center, and spread of distributions. And you say, well, when we talk about a normal, you would say, what's the shape? Then you would say, well, bell-shaped. Okay, and that's going to be synonymous with normal. You can kind of call that the shape normal. What's the center? Well, whatever mu is. What's the spread? Whatever the standard deviation is, right? We didn't talk about this a lot with binomial, but we could have done the same thing there too, right? You would say, well, what's the shape of that? Now, we didn't dive into this, but the shape of a binomial is going to be either symmetric or skewed depending on what the two parameters are. So we could have identified that. We could have gone down that rabbit hole if we wanted to. What's the center? Well, the center would have been the mean. How did we find that? N times p. What's the spread? Well, that's standard deviation. We could have found that by square root n times p times 1 minus p. We did that in some of the problems. So we didn't focus it then, but I want you to take note that we could have, right? So just make sure you're catching that when we talk about the binomial and the normal, we can talk about shape, center, and spread. We didn't do it a ton with binomial. We kind of focus more on probabilities, but we will do it a lot here with normal, because when you say normal, you've already said the shape, and center spread are just what the two parameters are, mu and sigma. And again, you say, how do I know what those are? Just like with the binomial, you couldn't come up with n. That had to be in the problem, right? The problem had to tell you what the sample size was. You couldn't magically come up with p. It had to be given to you in the problem. Now, it could have been a situation where it didn't tell you p, but it gave you enough information to find p, right? I could give you a binomial situation, and I can say, I'm interested in rolling a die, and I'm going to record it as a success if I roll a 2 or a 5. And you would say, oh, well, the probability of success is 2 out of 6. There's 2 ways I'm successful out of my 6 total options, right? So it didn't tell you P straight up, but it gave you the information to find P. So you had to be given in. How many times did you roll the dice? Had to be given to you in the problem. And P was either given to you in the problem, like in the call center example, right? How many times are you successful? 1 out of 10. Boom, there's your P. Or something like a die situation where you could say, oh, I know how many numbers on a die and I can find that probability easy. That stuff had to be given to you in the problem, and the same thing's going to hold true here. You're going to have to be given mu and sigma from the problem. Okay, so you don't have to come up with anything. You don't have to check anything off. You just have to read through the problem and pull out the correct information. Now, we've gotten this far in the lecture and we haven't actually covered the standard normal distribution. And that's why we're here for this section. We just kind of wanted to give an overview of continuous distributions. What does normal mean? It just means bell-shaped curve. We're going to focus in on the standard normal distribution, which is a subset of normal distributions, before we zoom back out and talk about all normal distributions. And the reason for that is that all normal distributions are a little bit more complicated. There's an extra step involved. When we start with standard normal, it's a little bit more straightforward. So any normal distribution can be standardized using The following formula that I'm going to give up, and you should already be thinking about what this is because we talked about how to standardize back in chapter 2. So this might be a good time for you to think through that. Pause if you want to. You don't have to go back and look, because I'm going to tell you in just a second, but just stop and think if you can recall. And these are the types of things you need to be able to recall. We covered in chapter 2 that when we standardize a value, that's value minus mean over standard deviation, and that is a z-score. Okay, and so it's by the formula z equals x minus mu over sigma. I want to make sure you catch this isn't necessarily something we're going to actively do in this section. In this section, everything that we have will already be a standard normal distribution. We're going to use this actually for next section. We're just kind of introducing the concept of how did we ever get there in the first place, right? How do we work with this? And it's this idea that we standardize by taking a value, subtracting the mean, divided by the standard deviation. And so if we have a normal random variable that has been standardized, we say this is a z distribution. So we've talked about the binomial distribution as a subset of discrete variables. We've talked about the normal distribution as a subset of continuous variables. And now we have a standard normal distribution as a subset of normal distributions. And that is called a z. So a couple of things here. Make sure you know that z and standard normal are synonymous. Not z and normal. That's not true. Z and normal are not synonymous. Z and standard normal are synonymous. Make sure you understand normal is the shape. When we add the adjective standard, that tells me more information. That's like saying you are a student at this university. That is some information, but there are lots of people who are students at this university. But if I add enough adjectives, like say your student ID number, that makes you unique, and there is only one of you that has this student ID number at this university. That's what that adjective standard is doing. Okay, when we add the adjective standard to normal, we're saying it's a unique normal distribution. And notice if you go back to the top of the page, we said a normal distribution just has a mean of mu and a standard deviation of sigma. It's whatever it is. Mu can be anything. Sigma can be anything that's positive. It can't be negative. But when we talk about a z distribution, it's a specific type of normal distribution. It's one that has that same bell-shaped curve, but it doesn't have a mu of whatever the problem has. It has a mean of 0, and it has a standard deviation of 1. Okay, so very important, that second bullet point. Make sure you understand that right there.